Now, this segment is one, as you see, for Unit 4, and it has to do with finding certain kinds of zeros of a polynomial. How can you find rational zeros, if any, of a polynomial function? The reason it wasn't in Unit 4 proper is because it's a really specialized technique that's not very useful in general, although it's nice and mathematically interesting, so I thought I'd put it in here so that you'll see how it works. All right, how do you find the rational zeros, if any, of a polynomial function? First thing I want to note is the specialized nature of the result we will eventually show you. The results here, and I'll repeat this later, the results here apply only to, well, they're always real polynomial functions, to real polynomial functions. But here is the interesting point, the point that's different and not general. Only applies to real polynomial functions with integer coefficients. So this only applies to the integer coefficient case. So if you have coefficients that are fractions or coefficients that are irrational numbers like square root of 2 or pi, etc., this will not apply. So this applies to those with integer coefficients, meaning, just to remind you, from z, the set of integers, which is the set 0, plus or minus 1, plus or minus 2, etc., out to infinity. So that's the first point to be made about this result. Now, in order to show you how this works without doing the proof in general, let me give you the idea that lies behind this. And the idea I will show you in the n equal 2 case, which is the first case where it becomes interesting. And the n equal 2 case is when we have a polynomial of degree 2. So we're talking about ax squared plus bx plus c, and we're assuming that a, b, and c are in z, the integers. Okay, so that's the situation we have. Now we ask the following question about rational zeros. What properties would a rational zero, okay, a rational zero of our f of x here, a rational zero, say p over q, where p and q are out of the integers, have? Okay, what properties would such a rational zero, get my 0 there, have? Okay? Now, we will assume, for the purposes of keeping things clean, we'll assume right from the start that we're only looking at p over q in lowest terms. That is to say, so p and q have no factors in common. Okay, we'll assume they have no factors in common. So we're dealing with the simplest possible version of the 0. Okay, well, the answer is the main property can be found this way. Since p over q is a 0 of f of x, we have the following. If it's a 0, then it needs to satisfy f of x, which means it can make f of x equal to 0. That's what 0 means after all. So that means that 0 is equal to a times the 0 here, p over q squared, plus b times p over q plus c. Okay? That's what being a 0 means. Well, let me multiply this out. What I have then is a p squared over q squared plus bp over q plus c, period. Now let me do a little bit of algebra here. Let me multiply through the entire expression by q squared, which is that largest common denominator. And I then get 0 is equal to a p squared plus bpq plus c q squared. Okay, that's what I end up with. Now I'm going to modify this in 2 different ways. And let me see if I can schematically indicate that. First of all, I'm going to take these 2 terms and move them over to the other side. And I'll call that version 1 that I want to modify, leaving ap squared alone. Then in the other one, I will take these 2 terms and move them over to the other side, and I will refer to that as version 2. That will leave cq squared alone. So I'm going to do that on the next page. First I'll do 1, and then I'll do 2. So here I want to observe what happens in each of these cases. For 1, if I move those across, I end up with AP squared being isolated, and on the right I have minus BPQ minus CQ squared. And on the right I can factor out the common factor Q, so I have Q times minus BP minus CQ, period. Now observe from this, Q divides the right-hand side, okay, because Q is a factor there. Therefore, it must divide the left-hand side because the left and the right are equal. Now, Q cannot divide into P because P and Q have no factors in common. Therefore, Q must divide into A. So, Q divides A. And remember what A was. A was the leading coefficient of our polynomial of degree 2 here. Okay, so we've learned that Q divides A. For 2, that's where we isolated CQ squared. So we got CQ squared is equal to then minus AP squared minus BPQ. And on the right, this time I will factor out the P. So P times minus AP minus BQ, period. Now look at this. Since P divides the right-hand side, P must also divide the left-hand side. But P and Q have no factors in common, therefore P must divide C. So P divides C, and what was C, remember? C was the constant term, or the constant coefficient, let's call it constant term. So what we've discovered is that if, in this little idea generation, that if P over Q is a root, or a 0 of our polynomial, then the bottom divides the leading coefficient and the top divides the constant term. And that works in general and leads us directly to the following theorem, which is what this section is about. This is called the Rational Zeros Theorem. Rational Zeros Theorem. And it goes like this. If, now we have to write out our real polynomial in general, so we've got that again. If f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 down to a sub 1 x plus a sub 0, where, as usual, n is equal to 1, 2, 3, etc., and the leading coefficient is non-zero, and we continue with properties we didn't have before. We assume now that the constant term is not 0, and we assume further that all of the coefficients, a minus 1 down to a0, are integers. So I'll even box this part in because that is totally new. We haven't had that in a statement of a theorem about polynomials before. If we have all of that and we are looking at P over Q in lowest terms, of course, P over Q in lowest terms is a rational zero of our f here, then what do we conclude? If we have such a rational zero, we conclude that the top of it, P, must divide a sub 0, which is the constant term, and it must also be true that Q, the bottom, divides a sub n, the leading coefficient. Let me write that again. A sub 0 is the constant term. That's what the top needs to divide. And a sub n is the leading coefficient. That's what the bottom needs to divide. So we can use this theorem, which I will not prove in general. We can use this theorem as a way of discovering various rational zeros, because every rational zero has to have this property. So if we look at all the numbers that divide a sub 0, they are potential numerators or tops for the rational zeros. And if we look at all the divisors of a sub n, we find all the potential denominators or bottoms. Now, in addition to that theorem, I'm going to give you another theorem. I'll call it the handy No Rational Zeros Theorem. Now, this is one that you don't often see in this course, and I think it's a very handy theorem. And since the Rational Zeros Theorem, as you will find out, can be quite tedious to apply and check. This at least will give you the chance to find out if there are any at all worth checking. So here's how the theorem goes, this no rational zeros theorem. If f of x is as given above, so we're talking about a real polynomial whose constant term is non-zero and all of whose coefficients are integers, is as given above, and the degree of f is greater than 1, so the only case left out is the linear case, so it's got to have degree greater than 1 for this theorem, and a sub 0, the constant term, a sub n, the leading coefficient, and f of 1, which when you think about it, if you put 1 in for all of the x's, what do you get? You just get the sum of the coefficients, an plus an minus 1 plus all the way down to a sub 0. If all of those are, if those are all odd numbers, okay, if they're all odd numbers, then you can immediately conclude without any work that f has no rational zeros. Now I won't prove this theorem either, but it is extremely handy, as you can expect, because it's very easy at a glance to see if a0 and an are odd, and f of 1 is just add all the coefficients together. That's not very hard either. So it's very easy to check whether this condition is met, and if this condition is met, then the function has no rational zeros, so you need not bother looking for them. All right, once again, here is the basic idea for looking for rational zeros if you want to do that. If this is your polynomial f of x equals a sub n x to the n plus dot 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 plus a sub 0, and if you have p over q sitting here being a rational zero, then what must happen? The p must divide, it divides a sub 0, and the q must divides a sub n. Okay, so if you have a rational zero like that, that is what has to happen, and so that gives you the test for checking rational zeros. Now my recommendation on using these two is, the first thing is check the second theorem first, because if there are no rational zeros, you don't want to spend your time looking for them. So check the second theorem first, and let me warn you, the list that the theorem allows for, the list of candidate zeros, candidate rational zeros, is often very long. Okay, we'll do a simple example here, but as you'll see, even in this example, things are quite tedious, which is the reason that this technique is not used all that often. So here's my example. List all the candidate, I'll call them candidate, you can call them proposed zeros, etc., or possible zeros, the candidate rational zeros of the following: f of x equals 2x cubed plus 11x squared minus 7x minus 6. And when you're done with that, check which are actually zeros. Okay? So let me box in my polynomial here so it'll stand out from that. The solution. All right, what do I want to do here? I want to find out all the candidate rational zeros. Let me notice a couple of things before I go on. This is a cubic polynomial, polynomial degree 3. Now that's fairly small, so we should expect, based on our knowledge of zeros, no more than 3 rational zeros. In fact, based on the pictures of cubics, we expect either 1 or 3 rational zeros. So, just keeping that in mind, let's go ahead and see if the rational zeros theorem applies. The coefficients, all integers, as you see, 2, 11, minus 7, and minus 6, so the theorem will apply. We also see that an is not 0 and a naught is not 0, so the theorem indeed applies. Now we know that p of a potential p over q rational zero, p must divide, or divides, a sub 0. So what are the candidates for p? All the divisors of a sub 0 minus 6. Those would be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And let me point out here, don't forget the negatives. Don't forget the negative cases. Okay? Because negatives can be rational numbers. They can be the top of a rational number. Now, finding all of these sometimes can be hard. If the number is rather large, you might have to do a lot of extra work to get all the factors. This one was easy. And then also q must divide a sub n. Well, a sub n is 2, so this is a little easier. We know that plus or minus 1 and plus or minus 2 will then divide that. Now, of course, we're not interested in p or q alone, so we are interested in p over q candidates. So the candidates for p over q are taking these p's over these q's. Well, first of all, any of the p's over plus or minus 1 will preserve these. They'll change the sign, but we have plus or minus, so it'll become minus plus. So these over 1 will give these back. So we'll just repeat all the integers there. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Then the p's divided by the 2's will preserve their plus or minus, but let's see, we gain some new ones. 1 over 2 gives us plus or minus 1/2. 2 over 2, of course, is 1, which we already have. 3 over 2 is a new one, plus or minus 3/2. And 6 over 2 gives us 3, which we already have. So here are all the candidates for rational zeros. That's 1, 2, 3, 4, 5, 6 times 2. That's 12 candidates. Now we know that at most 3 of these are correct. It would be very tedious to try and substitute every one of these into the original expression. So I'm going to use what other information I know to help me reduce the tedium. So it's tedious to check 12 candidates. So we graph the function to help narrow our choices. Now if you graph this is the window I use, minus 7, 3 by minus 10, 70. If you graph our cubic, here is the picture that I got. Here is the axis. There's another axis. I come up here and it goes like this and then comes down there and goes up there. So it looks like I have 1, 2, 3 zeros. And if I then use trace or some other means, I see that this is approximately minus 6. This one is approximately minus 0.5. And this one is approximately 1. Now those are all members of my collection of rational candidates. This is 1/2, minus 1/2, this is 1 and minus 6. It turns out, if we check these, that they all work. F of minus 6 is 0, f of minus 0.5 is 0, and likewise f of 1 is 0. So the only 3 rational zeros are those, and that covers all of the zeros, so we're done as far as finding zeros go. That eliminated 9 candidates. So using graphing or any other technique, in addition to what you already know, may help. All right, let me do one example to show you the advantage of that second theorem. Here's my example. And the question is, any rational zeros? And here is the polynomial f of x equals x to the 5th plus 7x to the 4th minus 28x cubed plus 125x squared plus x, and finally minus 3,275. Now, no one in his right mind would want to try the rational zeros theorem on this, because you would be looking for all the factors of 3,275. So the smart thing to do is to see if there are any rational zeros at all using that second theorem. So let's observe that A5 is equal to 1, which is odd, okay? And A sub 0 is equal to minus 3,275, which is also odd. And then let's look at f of 1, which remember is just, when you put 1 in for x, you're just adding the coefficients. So the sum of the coefficients is 1 plus 7 minus 28 plus 125 plus 1 minus 3275. And if you drop that in your calculator, you get minus 3,169, which is odd. So all of these are odd, which means the conditions of the theorem are met. So there are no rational zeros. Therefore, you need not check all of the divisors of 3,275, because that would be very tedious. Okay, on that note, I will leave this little segment. I hope that added to your knowledge from Unit 4, and then I'll have one more segment to show you.